So today we are going to see the switching characteristics of the devices. For that we have to study what is the basic static characteristics of an ideal switch. So this is a graph, there is this a plot for the voltage versus current. That is, here the power semiconductor devices, all the power devices are used as a switching device. Either it will be in turn on condition or it will be in turn off condition. So this is in this case, first case, the first case represents the switch is in off condition. So during that condition, the current flowing through that switch is 0 and the voltage across the switch will be equal to the applied voltage, that is off time voltage, and the product of the voltage and current, that is the power across the switch, will be equal to 0. So that is during the off condition of the turn off condition of the switch. And in the graph, that is voltage versus current plot, we will have the only the x-axis, that is voltage axis, and we are having the voltage, and there is no current, that is current is equal to 0. And if you are turning on the device, that is for the fully controlled device, we are turning on the device by means of applying some gate signal, the device will suddenly goes to the on state. That is, during the on state, what will be the condition of the switch means the current through the switch will be equal to the full rated current, that is I is equal to I on, and the voltage across the switch which is equal to 0, that is voltage drop across the switch is equal to 0 for the ideal case, so that the power dissipation across the switch is equal to P on, that is equal to 0. So here, in the turn on condition, that is only current will be existing at higher the rated value and the voltage across the switch is 0. So during the turn off condition of the switch, only we are having the magnitude at the x-axis, that is voltage alone, and during the turn on condition of the switch, the current alone will be existing, that is full rated current will exist, and there is not be any value for the x-axis. So off condition, the voltage will be existing, current is 0, and during the on condition, current is existing, voltage will be 0. So that will be that is also possible in case of the third quadrant, that is negative side. That is, this first quadrant is for the turn off position to turn on condition, and the third quadrant is for the turn off position to turn on condition. So turn on position to turn off condition, both can be reversed. So when the switch is off, the current I is equal to 0 and the voltage will exist between minus infinity to plus infinity, which implies the product of the voltage and current, power dissipation across the switch is 0. And during the turn on condition of the switch, V is equal to 0 and current exists between minus infinity to plus infinity. It is for ideal switch. For normal practical cases, there will be some definite magnitude from minus to plus, which implies, and the product of the voltage and current, that is power dissipation, is also 0. So it is possible to easily turn on the switch and off the switch by applying appropriate control signal. The power terminals of the switch should be electrically isolated from the control terminals. So this is the basic of the turning on and turn off the switch. So in turning on and turn off process, here we can say that during turn off condition, the voltage across the switch is full value applied, full voltage, and the current is equal to 0, and during the turn on condition, the current is at full rated value and the voltage is 0, and the transition takes place from off to on or on to off will be in a fraction of second, that is in 0 seconds it will happen, but in practical cases it will not be there, so that will take some time, or there will be some transition time for the turn off process to turn on process, and also from turn on process to turn off process. So for the transition, we have to study the switching characteristics of the devices. So the switching characteristics can be called as the dynamic characteristics of the devices. So here the first plot represents VD is the voltage across the device and ID is the current through the device. So at the time t is equal to 0, so the device will be in off condition, so the voltage will be existing and current will be 0. And after some time we are applying some by means of gate signal, the device gets turned on. So in ideal cases, the voltage across the device suddenly comes to zero, and the current flowing through the device will suddenly increases to the rated value ID. But in practical cases, it will take some switching time, that is for the rise of current from the zero to the maximum value, and for the fall of voltage from the maximum value to the minimum value. So at particular condition or for a certain period of time, both the parameters will be existing, that is the current is gradually increasing and the voltage across the device is gradually drops to the minimum voltage, that is voltage drop across the device. So at the time of TSW, that is a switching time of the on period, that is a switching time of on condition, there will be this is the period for the existing of two parameters, voltage and current. So for the product of voltage and current will have some the IDS into VDS, so that will be equal to the switching losses. And during the fully turn on condition, we will have the maximum current value and we will have some minimum amount of voltage, that is ID into RDS on. RDS on is nothing but the resistance of the device at the on condition. So for the ideal case, the RDS will be equal to 0, and for the practical case there will be some resistance of the device. So due to that resistance, so there will be some minimum voltage across the device. So that minimum voltage and the product of the current will produces a loss called conduction losses. So the conduction loss will be existing at the time of turn on condition, that is a fully conducting state. And after that we are turning off the switch by means of removing the control signal. So at that condition the voltage has to be increased to the maximum value of VD, and the current has to be decreased from the maximum value of ID to the 0. So this will also take some transition time, that is the switching time for the off period. So TSW off, it is nothing but the turn off time. So for the turn off time, the voltage will rises to maximum and current will reduces to 0. So for the switching time off, we will have some we will have the both the parameters existing. So for that we can have the product of voltage and current. So there will be some switching losses. So during the process of turning on and turn off the device, we will have the for a certain period of time both the parameters will be existing at higher value. So at that condition some losses will be occurring. So that losses is considered as switching losses, and the losses which is occurring during the conduction period is called as conduction losses. So this is the overall or the general graph for the switching characteristics. So the switching characteristics nothing but the during the turn on and the turn off period, or from the transition from turn on to turn off or turn off to turn on, we will have some period for the for the transition of one period to another period. For the turn on to turn off or turn off to turn on, we will have some transition time. So that is called the switching time. So that switching time will decide the switching losses. So first we can see the transistor, that is a BJT switching characteristics. So the first graph represents the base emitter voltage, that is the voltage applied across the base to emitter, and the here the driving or the controlling control signal is the base current. This, since the transistor is a current controlled device, so when we are applying the VBE, that is base emitter voltage, the base current is flowing through the transistor. So at the instant of starting the giving the VBE, that is base to emitter voltage, the base current starts flows, and the magnitude of the current will be equal to IBS. And at the instant of giving the base current, the turn on process is initiated, and up to that, so there will be some current will flow through the device. So that is due to the minority carriers, that is the leakage current will flows, that is ICE naught, and TD is the delay time. So delay time, after the delay time only the current will starts to increase and voltage will starts to decrease. So the delay time is to charge the base emitter capacitance to the VBES, that is 0.7 volts. So that is the time, that is the TD is the delay time to charge the base emitter capacitance to 0.7 volts. So after that the current of the collector current will increases from the minimum value, that is the leakage current, to the maximum value of ICS. that is called rising time, and at that time the voltage is falls from the maximum value of VCC to the value of VCES, that is the voltage across the device, that is voltage drop across the device. And the Tn, that is T on will be equal to Td plus Tr, that is delay time plus rise time, and that is the total time required for the turn on of the device after applying the base signal. So after that we are having the Tn, that is the total on period of the device, and after that the turn off process is initiated by removing the base emitter voltage, and the base current is also 0. So at that condition we are the turn off process is initiated. So during that condition that will take some time to completely turn off the device. So that is nothing but the turn off turn off time will be equal to Ts plus Tf, that is storage time and fall time. The storage time, after the storage time only the current will starts to decrease and the voltage will starts to increase. So the storage time is the time required for the trapped charges to gets removed, or the saturation charges to be gets removed from the base of the transistor. So that is the storage time, that is to remove the trapped charges. And the fall time Tf, the fall time is the time taken for falling of the current from the maximum value to the minimum leakage current, and the rise of voltage from the VCES, on state voltage across the device, to the maximum value of VCC. So this is the switching characteristics of the transistor. So here it is explained, that is turn on time is equal to Td plus Tr, that is delay time and rise time. Td is equal to delay time, that is IC is equal to IC not collector to emitter leakage current. VCE is equal to VCC. So during this condition delay time, the current will be ICE naught minimum value of current, and VCE is equal to VCC maximum value of voltage, and this is the time required to charge the base emitter capacitance VBES, that is 0.7 volts. And next one is the rise time, that is the time taken for the rise of current from minimum value to the maximum value, and VC is the fall of current from the maximum value to the VCS. And the turn off process, that is the turn off time will be equal to T off is equal to Ts plus Tf, that is storage time and fall time. During the storage time the IC is equal to ICS, and VC is equal to VCES, and after the storage time the current will start to decrease and voltage will start to increase. So the storage time is the time required to remove the charge from the base, that is to remove the trapped charges or to remove the saturated charges from the base. And TR is the fall time, sorry, TF. So here it is, it should be, it is a spelling mistake or the typing mistake, that is TF is equal to fall time. That during that condition the current will fall from the maximum to minimum value and voltage will rise from the minimum value to the maximum value. And the next one is the switching waveforms, or the switching characteristics of the MOSFET. So MOSFET is a voltage controlled device, so we have to apply the gate signal as the control parameter. But after applying the gate signal, so the characteristics, that is the turn on process, will be initiated. So first one, the MOSFET switching characteristics is influenced by the internal capacitance and the internal impedance of the gate drive circuit. And first one, if the VGS is applied, that is VG is the gate gate voltage, and VGS is the voltage applied across the gate and source. So after the application of the VGS, there will be some delay time, that is TDN. So TDN, that is voltage, gate source voltage is increased from the 0 value to the VGST, that is the VGST is nothing but the threshold gate source voltage. So the voltage will rise from the 0 to VGST. So that is the time required to charge input capacitance to the value of VGST. That after that time only the drain current will increases from the 0 to the maximum value of current. And TR is the rise time of the drain current, and during that condition we have to increase the gate source voltage from the threshold voltage to the sufficient voltage, that is VGS peak, that is VGSP, that is the VGS peak, that is the sufficient voltage to drive the MOSFET to turn on condition. So after the application of magnitude of the voltage as VGSP, that is we are increasing the gate source voltage from the threshold to the peak value. So at that condition, the MOSFET will fully drives to the on state. So that is the rise time, that is from 0 to the current drain current will rise from 0 to the maximum value of ID. And after that, at the instant of T1, the turn off process is initiated. The turn off process is the removal of, after the removal of gate source voltage, we are having the turn off process, that is turn off time will be equal to TDF plus T TDF plus TF. So TDF is nothing but the delay time and TF is nothing but your fall time. So that is the TDF is the time required to discharge the input capacitance from the value of V1 to VGSP. So in the time of TDF, that is the delay time during the off condition, the voltage of the gate source voltage is decreased or discharged from the maximum value to the VGSP, that is the discharging of the input capacitance. And TF is the fall time, the input capacitance discharges from VGSP to VGST, that is threshold voltage, peak value to threshold voltage. And during that condition, the current TF during that time TF, the current will falls from the ID maximum value to the 0 value. So this is switching waveforms for the explanations. That is turn on time is equal to T on is equal to TDN plus TR, turn on delay time. During that time the input capacitance charges to VGS threshold and ID is equal to 0, and after this end of the time the VGS will be equal to VGST, that is VGS threshold, and TR is the rise time, that is VGS is raised to the VGS peak value, and during this condition the drain current will rises to the maximum value. And switching waveforms for power MOSFET, that is turn off time T off is equal to TDF, turn off delay time plus fall time, and during this condition input capacitance discharges from the maximum value of V1 to VGSP, and the current will be the same value, that is maximum current, and fall time, it is the time required for the discharging the capacitance from the peak value to the VGS threshold voltage, and during this condition the current ID, drain current, will falls to 0. Thank you.